In this video, we will take a quick look at something called the trapezoidal rule. So when we did the rectangle approximation methods, we used rectangles to approximate under the curves, but you notice, and there are over approximations and under approximations depending on whether the curve was increasing or decreasing. But in this set of notes, we're going to learn to, instead of using rectangles, use the area of trapezoids. And again, the goal is to put a bunch of trapezoids in here to get a better approximation. So you can imagine if all of these were, left hand rectangles, it would be a lot different, or right hand rectangles would be a lot different, but the trapezoid allows it to follow the curve a little bit better than what rectangles would. On the assignments, make sure sometimes it'll ask you to use the Simpsons rule as well, but we're just focused on the trapezoidal rule. All right, so what is the trapezoidal rule? Well, like I mentioned, instead of using rectangles, you are using trapezoids. So if you think back to the area of a trapezoid, right? So imagine for me, thinking back, what is the area of a trapezoid? Draw one. Here we go. All right. So if you can go ahead on your own, let's figure out the area of this trapezoid. So you have the base and the height. Go ahead and see if you can remember what the area of a trapezoid is. In this case, it's going to be a little bit different. You're used to trapezoids that are more stereotypically like this, right? So ours is going to be a little bit different, right? So you do have your base, but then now you have your two heights, whereas in the typical definition of a trapezoid, your two heights would be your two bases that you would add together, because generally it's base 1 plus base 2 times the height divided by 2, right? So this is going to look a little bit different than that. It's still going to, you're still going to have to figure out what this distance is. But when we're looking at a graph to find this distance, it's x sub 2 minus x sub 1, right? But in our formula, we're going to use x sub 1 as a, x sub 2 as b. And then also, you have your function here. This is your height. So if we wanted to know what this height was, that point right there, that is f sub x sub 1. Or f of a, right, to give you your height. And this would be f of x sub 2 or f of b. All right, so that would give you your two heights in this case. So you have your two heights or your bases, like what you in the typical formula that you usually use, and then your height is the b minus a to find that height. Now here's the other trick that we have to incorporate is the fact that we're finding the areas of all of these, right? So now if you look at the next one, it includes this same height, f of x sub 2, and now we have this other one, f of x sub 3. All right, so we're coming up with one formula where we can find it for all of those trapezoids within that range, okay? And this range would be however many trapezoids you break up, the number of trapezoids you have would be considered n. Right? That would be the number of trapezoids. So now let's look at this rule coming from these ideas of the area of one single trapezoid. The rule, I wrote it two different ways. If you need to pause it, go ahead and pause it periodically as you get this written down. But let's look, and it applies to this right up here. We're looking at this. So f of x is that curve, right? And we're trying to find the area under that curve. So here's the integral. There's the exact integral, but again, let's say that we don't know how to integrate f of x. Well, we have to find a good approximation and enter trapezoidal rule. So here's your b minus a. That is the height of every single trapezoid over the 2n So with the trapezoid, it was always divided by 2. It was the sum of base 1 plus base 2 all over 2. And then the n is just the number of trapezoids that you have in there. So if you have 12 trapezoids, it's over 2 times 12. And then all of this represents your heights. Now you notice the very first and last heights are not multiplied by 2. That's because they're only included in this formula one time. All of the other heights are a part of 2 trapezoids. So that's why it's plus 2 times f of x sub 1, because it is, f of x sub 1 is both the higher height of the first trapezoid and the lower height of the second trapezoid. Right? So it's always times 2 to all of your middle heights, but not your very last heights. And remember that n, so this is h sub n, and x sub n, that is if you have 12 trapezoids, that would be your 12th height, your very last height, whatever that would be. Okay, so again, if you need to pause the video, do that right now, and make sure you have n is the number of trapezoids that you have in that given interval. Now let's take a look at an example. The trapezoidal rule to approximate sine of x between 0 and pi. And we're going to do it when n is equal to 4 and when n is equal to 8. So using this formula above, go ahead and pause the video and see if you can't try and do this one on your own. And when you're finished, unpause the video, come back and see how you did. All right, now let's take a look at how we did here. First of all, it might be easier to figure out what are your x subintervals, meaning, okay, if we're going from 0 to pi with 4 subintervals, right, what are the x values that I'm plugging into? I have to grab the highlighter. What are the x values that I'm plugging in to my function? Might be easier just to come up with those right off the bat, because if it's 4 subintervals and 0 to pi, well, it's 0, pi over 4, pi over 2, 3 pi over 4, and pi. So we set it up. Remember, we're approximating this using the trapezoidal rule, so it's b minus a, pi minus 0, all over 2 times n, and that's where the 2 times 4. And that simplifies down here to pi over 8. And then remember the first term and the last term, we only use those sides of those trapezoids once, so they're just times 1, but all of the other ones, the 3 in the middle, are times 2, okay? And then when we simplify those down here, the sign of 0 is 0, the sign of pi over 4 is radical 2 over 2, the sign of pi over 2 is 1, the sign of 3 pi over 4 is radical 2 over 2, and the sign of pi is 0. And then when you multiply these by 2, the middle ones, those will cancel, so you would just get radical 2 here. Those will cancel, so you just get radical 2 there. So you have radical 2 plus radical 2, and that's where this radical 2 comes from, and then you just have plus 2. Okay? So that is our answer, but we can go one step further and factor out a 2. And when you do that, you factor out a 2, it will simplify with that 8, and I'll show you. So you'd have 2 pi over 8, then you would just have radical 2 plus 1, and that 2 pi over 8 will simplify just 2 pi over 4. And that is as far as we can go on that one. So that would be our best trapezoidal approximation with these intervals of n being 4. Now let's try it when it's 8. Again, come up with your intervals first. That might be a little bit easier, and then use the trap rule. In setting this up, our intervals are as such. You have 0, pi over 8, pi over 4, 3 pi over 8, pi over 2, 5 pi over 8, 3 pi over 4, 7 pi over 8, and pi. So we have to plug all of those into the sine function. And remember the middle ones, then you multiply by 2. And the very first and the last, which are going to be 0 anyway, so I guess it doesn't matter. You don't multiply by 2. And your b minus a over 2n, that's pi over 16. in that case. And from here, you simplify. You should find the pi of all of those and then simplify after that. So some of these are, we know from above, but some of these you just plug into a calculator, sine of pi over 8. It's not one that's necessarily on the unit circle, but be careful when you're plugging, if you're plugging all of these in the calculator at the same time, your answer should be, and once you multiply it by the pi over 16, your answer should be 1.974. 1.974. Which is a closer approximation than what we had up there, which if you plug the pi over 4 times radical 2 plus 1 into a calculator, you get 1.896. So it's a closer approximation since we're using more trapezoids. But as you can see, it's a little bit more work to get that answer there with 8 of them. Okay, so that's it. That's all we are doing out of this section is the trapezoidal rule. The Simpson's rule is very different, but it's an even closer approximation. But again, we are not going to go over the Simpson's rule, but if you're interested, it looks very similar to it, but it adds one unique twist. But that's it for this set of notes.